Hello, hello. Okay, so I hope you are enjoying TechFest. And now I introduce you how to protect yourself from the biggest internet threats by Ignat Korchagin. An applause.
Hola, my name is Ignat. I work for Cloudflare, and today we're going to talk about internet attacks. So, who here is familiar with Cloudflare? Who uses Cloudflare? Thank you very much. And please complain if something doesn't work. A little bit about myself. I work on Linux at Cloudflare, the operating system itself. I'm a diehard Linux fan. That's why I'm presenting from a Mac, but you can ask me later. I'm into operating system infrastructure, security, and performance, and I also enjoy low-level programming like Linux kernel, drivers, bootloaders, and other stuff written in scary, unsafe languages. Yeah, but today we're going to talk about internet attacks. And let's start about just trying to grasp what kind of like modern internet attacks look like and like what are they, right? So first let's talk about distributed attacks on the internet. So let's start simple, right? Like not distributed, simple attacks. So like you have a server somewhere on the internet, it provides some service to you, and you have users accessing this server at some point. And at some point, attacker comes in, right? So they start sending loads of malicious traffic to your server and eventually overloading the server so it cannot process requests in a timely manner. And then eventually what it looks like from a user's perspective, they can't access the servers and they become unhappy, right? Simple. So what do you do in this case? Well, and simply, you can design some kind of firewall and try to block the attacker from accessing your servers. And eventually, the server is not overloaded anymore, and your users become happy again. So this is like a simple attack, right? Now, how does it scale in the internet world? So like, your service is running on the internet. The problem is like, internet is big and like more attackers could come in, right? So like you can design a firewall rule to block that specific IP address, but then attacker can attack from other IP addresses, and again, your server becomes overloaded. What is the typical approach most people take here is, well, they hide their servers from the internet and put some kind of like a bigger firewall in front, right? Some kind of but the problem is internet is big, right? So like more attackers can come in, and then again, your dedicated firewall becomes really overloaded. Now the mistake here is that many companies like say, oh, we can't solve this on our own, we'll go and search for some kind of outside support. And what they do is like there are like security vendors out there who say, hey, instead of like just regular another computer box, we have this dedicated firewall which is like fine-tuned to really be powerful, and it's often quite expensive, right? So like use that, and you can use that, and for some time it kind of helps. But again, internet is just too big. So like more and more attackers comes in, and eventually, if there is a really huge attack, they can still overload even that expensive firewall. And you will lose your service, right? So why does it happen? The problem is with largest distributed internet attacks that the attacker scales their attack horizontally. So how does attacker get like more computed? Often they exploit some vulnerability, either in like vulnerable servers across the world or like some IoT devices, which is mostly happens. So they capture a lot of compute around the world. It's very distributed, and they can acquire the more compute very cheaply because it's basically getting for free. This approach, kind of like the hardware box approach, requires you to scale vertically, right? So the attack is like scales very fast and horizontally cheaply, but you need to buy more expensive and powerful boxes, and basically the cost grows exponentially now. So like it's not and small incremental cost. So the first takeaway from this talk is that you need to scale the same way as an attacker to provide an efficient defense. So yeah, to efficiently protect from global distributed internet attacks, you need kind of a global distributed internet defense. And yeah, and so in extreme cases, hardware boxes will not work, and you need to find a way to scale horizontally with the attacker. So how do we do it? First, let's get into basics. So let's talk about internet addressing. So Unicast, we use it every day. So you have a server, it has an IP address assigned, and basically if users want to reach your service, they type in a browser something or an API or in a client, and kind of that traffic routes to your server because the internet knows that this server has this IP address. So how do you scale horizontally the system, right? So most of the time, what we see in like middle to large setups, so we try to scale it, but we still do unicast with load balancing. So we put a kind of box in front which has this public IP address, and then we have like a couple of backend servers, right? And then like the traffic goes to this front box with IP address, and then it just shuffles in between the backend servers. And if you need more capacity, you just add another backend server, and it kind of works. But that kind of like it works for medium setups. It doesn't work on internet large scale, just because it's still you have this front box, which is a single point of failure. Who here is familiar with Anycast? How Anycast works? Okay, nice. So instead of Unicast, we use Anycast as a backbone of our network. So what Anycast means is like we have many servers across the world with the same IP address, right? Nobody said you can't have, it should be only one box with an IP address. And basically the magic of internet works in a way that if there are several resources with the same IP address, depending on where the traffic originates, the internet was designed in a way to route your traffic to the closest or the cheapest location. But in a nutshell, what it means that if there are many users across the internet, they will access different servers. So like for every parts of the world, their traffic would be routed to different servers. The nice thing about this property, it not only works for users, well, it also works for attackers as well. So if an attacker just wants to attack a resource, it's no longer, the traffic is no longer like routed to a single point. It's kind of like naturally, the way how internet designed to work is like distributed across the whole internet, depending on how many locations you have. So for example, this is like not so recent, but still network of Cloudflare data centers. And yeah, we have like a lot of them. And basically, it's a big Anycast network. So if there is a web resource behind Cloudflare, its IP address is announced to the internet from all these locations. So wherever the attacker traffic originates, it will be hopefully routed to the either closest or next to closest data center and served kind of locally. And this is how the traffic is naturally distributed. Yeah, so both user traffic and attack traffic are distributed all over the world. And as you can see in this schema, we don't need any specialized hardware, right? So we're just using the natural properties of the internet. And also, now we can really scale our network horizontally to consume different attacks, because we just keep adding more servers. Like the attacker adds more compute, and we can add more compute, and we can handle more traffic. And again, and our horizontal scaling not only allows us to absorb very large attacks on the internet, but also it's like service more users, right? Like by scaling horizontally, you get more capacity and you can handle more traffic. Clear? Cool. Now let's talk about internet hijacks, which often happen on the internet. So how does the internet work? What is the internet? The internet is a network of networks, right? They're independent networks. And these networks are usually defined by some kind of assigned number. So like this is like Cloudflare. This, I think this is Amazon or Google, something like that. Yeah, whatever. And yeah, these networks, they just continuously exchange traffic between each other, right? But how does, for example, like if a user is somewhere here or on this network, right, and it tries to access resource on Cloudflare, like how does it know that like a particular IP address belongs to Cloudflare? So like how does it network know that it should send that traffic here? And basically, it's the way how networks communicate between each other is called Border Gateway Protocol, or called BGP. Who here heard about BGP? Cool. In a nutshell, the way how it works is each network continuously shouts to the internet, called announcements, announce the IP addresses they own. So Cloudflare announces like this, one of the like IP ranges, but there are many others. And like networks continuously announce, and other networks listen to these announcements and know which IP addresses belong to these networks. Now you can already guess like what's wrong with the schema, right? So like internet was designed like a long time ago. Most of us even wasn't born, and it was kind of like a gentleman's agreement that, you know, if you own an IP address, you announce it. If you don't own, you shouldn't announce it. But like in modern security, there are like bad actors on the internet which just come and start announcing IP addresses which they don't own. And this what cause, like if that happens, like the traffic instead of going here might go here, right? And but so kind of like this is what called like BGP hijacks, that like the traffic does not go to the proper autonomous network, it's not processed properly, it's like in best case it's just black hole, and you don't get any service, and in the worst case you may have like a fake PayPal set up here to harvest your data. So how does modern internet tries to solve it? Basically now there is an update to the BGP protocol called RPKI. And what it requires is that the networks should sign their announcement, and other networks should verify the announcement. But well, it's still kind of a and this schema allows that like kind of like validate the announcement. So other networks, by verifying signatures on an announcement, they know this announcement is legitimate, and they know like this announcement is not legitimate, so they will not take it into account and will never send the traffic there. Unfortunately, it's kind of like a two-person agreement. So like not only you need to sign your own announcement, right? The accepting network actually needs to verify the announcements. If you can't make the other network verify your announcement, just take every announcement as in good old days, the schema will not work. And unfortunately, not every network these days is verifying BGP announcements. So we in Cloudflare developed this interesting tool like called isbgpsafeyet.com, where you can basically go log in and test if your ISP, the one you're currently using, is actually verifying BGP announcement. If it doesn't, like if you have any, you know, connection to them, like try to reach out and ask them to do so, because it will make the internet much more reliable. So yeah, this is my home ISP, unfortunately. And this is like Cloudflare network. Yep. Cool. And actually what I wanted to say is like verify, these announcements are not only happening just because like there's someone malicious on the internet. Like many times these hijacks happen like unintentionally, where someone somewhere misconfigures a network equipment. So not only this provides more security, this allows you to kind of like not take into account these misconfiguration, and like internet just becomes much more reliable and faster. So this is where like security brings performance as well. Cool. Now let's talk about another interesting case of how attackers try to attack resources, is like CDN bypass. So if you use Cloudflare or use any other CDN, you kind of know why you're using CDN in the first place, right? So you have a web resource, you hide it behind some kind of like CDN, and the idea is that well, apart from performance improvements that you get and caching and all that other stuff, you get the security benefits that the CDN, like your users kind of, instead of talking directly to your server, will talk to the CDN, and the CDN will pass on that traffic to your application. So, but it can also like cache some of the static content and stuff. But another option is like it should provide security filtering, where if an attacker talks to the CDN, well, kind of shouldn't pass this traffic to your service. So in fact, if you're using a CDN, you're kind of like, you don't have to have a very powerful box here. So like the whole power comes here on the CDN, which can like filter and process, pre-process the traffic for you. That's the whole idea. Yeah, but the problem with this setup is your resource still has an internet routable IP address, right? So what some attackers can do, if attackers somehow, like the regular users use CDN IP addresses for your web service, but if an attacker somehow knows your real IP address, they can just like do this. They can just send traffic directly to your IP address and bypassing the CDN. Yeah, and kind of break the whole system. This is very important, like because not everyone understands that once you are behind a CDN, you should treat your public IP addresses as some kind of secret information and make sure it doesn't leak, because there are different reasons for how attacker can learn it. For example, many times people configure their CDNs that like, static content passes through the CDN, but they don't want like API traffic, for example, to pass through the CDN. So they configure the CDN that the API traffic bypasses the CDN. And in this case, when an attacker just can resolve your API endpoint, it will know your real IP address because it didn't go to the CDN, because it was configured this way. So how can we do, what can we do in this case? Like, well, naturally, not to allow an attacker to access your service from the internet, well, don't put it on the internet. Yeah, run it on localhost, right? Well, it kind of like works, but it doesn't like how users access. What can you do now is that you can reconfigure the system in a backwards scenario. So technically, instead of the CDN contacting your service, like your server can establish like outgoing connections to the CDN, like so-called, we call them Agress tunnels. And once it's established, like when legitimate users and attackers access the CDN, so the CDN will use the existing connection to like forward the user request to your service, right? And of course, it will not forward the attacker's request. But the nice property about this, like this person here, how do they reach your service? Because it only, like your server is configured only to allow outgoing connections, and it's configured never to accept any incoming connections. Again, no specialized hardware here. Okay, now let's talk about data center level protection. So in this case, we talked about how we protect on the network side level, on the intranet level. But you may have noticed that we don't actually filter bad traffic anywhere here. We just try to slice and dice it, slice and dice it, slice and dice it, so it cannot overload a single location, but we never block it anywhere, right? So it goes around the internet freely. So let's go to one data center and see like what's happening inside. So what can you do in the data center? So again, based from the previous slides, your data center receives some portion of the user traffic due to Anycast, and of course some portion of the attack traffic. And again, the traditional data center design is what many folks do, is like it's kind of load balancer design. So they have the load balancer and a couple of backend servers so they can scale. But again, the problem with this approach that the load balancer is a single point of failure. So if there is too much attack traffic going to a single location, that might be overloaded, right? And again, you might be tempted to replace it with a huge, powerful, dedicated box from a very popular security vendor, but at some point it fails anyway. So what do we do instead? Well, we just reuse what we have. So our data center has a router, right? So like every data center has a router or several routers. So and inside the data center, and instead of having your service IPs on the load balancer, like every server has the IP address that we serve, right? And what we do is we use a technology called ECMP, which is kind of a in data center counterpart of BGP. So each server just announces to the router that I have these IP addresses. And the router will insist on this announcement, and basically if several servers announce the same IP address, it will like shuffle traffic between the servers. And it kind of like, it's helpful for us because again, it allows us to scale the data center horizontally. So if we want to add more servers, we just bring them online. They start announcing IP addresses, and the router automatically redistributes the traffic between all the available announcers, right? And it's also like very handy in the maintenance case. So if we need to put a server down for maintenance, so we just power down and it stops announcing, and the router naturally stops sending traffic to it. And again, it sends the traffic only to the servers which are online. And again, in this case, well, you kind of may say like router is a more dedicated equipment, but you need to have it anyway, but we don't have any like specialized boxes for DDoS protection in the data center. We just use the regular equipment that we have. Okay, now we talked about the data center level protection. Now let's zoom into the server layer. Again, in this schema, we're not blocking the attack traffic anywhere. We're just slicing and slicing and slicing and slicing to as many servers as possible. So where does the traffic get blocked, right? The bad traffic. So let's talk about how the server processes the traffic. So imagine your server receives bad traffic, right? And you want to handle it. Like, what about this? Like, anyone knows what this does? Yeah. So it's configured. It's a Linux firewall rule to block all traffic, all incoming traffic. Is that efficient? Well, at least for attack traffic, maybe, yes, but it's not very useful because the good traffic will not go through. But what if I told you, like, it's not even efficient for attack traffic? And the reason is the following. So again, we have our server. We have good and bad traffic coming in. So what happens actually inside the server? So a network packet arrives and it's received by your network card, your network hardware, right? So the network card issues a hardware interrupt to the operating system, to the main CPU, and starts to talking to network card driver in the operating system, right? And what does the driver do? In Linux, it allocates a data structure called SKB, which is like an in-kernel representation of a packet. It's a buffer. It's kind of a huge structure, and over here there are like many fields there. It also copies the packet data and re-enables interrupts. So like we need to service interrupts faster. So we copy the data from the link, re-enable interrupt. Then the driver passes this SKB struct with the packet to the data link layer. You know, like the network OSI model. So, and here what happens is, well, many things happens here. So what this does is like parses L2 headers, the MAC addresses, like calculates L2 checksums. It may like merge adjuncts and frames for better efficiency, and so on, so on. And then when it does, it passes this structure to the network layer, and the network layer kind of does similar things. It's it parses layer 3 headers, does connection traffic, layer 3 checksumming, counting, and only then, if this was an attack traffic, and if you have like drop everything firewall, it drops the packet. So like it did all this thing just to drop the packet here, right? So we actually proved in real case scenarios that if you have a server with a block everything incoming, every traffic, if you flood it with enough packets, you can still overload it, just because this thing happens. So what we need here is like not to do all this work for bad traffic. And what we adopted in Cloudflare is technology called XDP, Express Data Path. So it's an open source technology. It was, well, not so recently already emerged into the Linux kernel. And what it essentially does, it allows the operating system to inject small eBPF programs early in the packet receive parts. Anyone here heard about eBPF? Yeah, so eBPF is a new hot thing in Linux. It gives you security, it gives you tracing for performance, and it also gives you like really great network processing. So eBPF is fast, is programmable, so you can actually, instead of like configuring your rules, you can write almost arbitrary programs to validate packets. It's safe, so eBPF guarantees that no matter how bad you're a programmer, you cannot, even though it runs inside the Linux kernel, which is very scary, it cannot crash your kernel. So if you basically have a bad program, the kernel will just not accept it. And yeah, and here is a link to the documentation. So, and XDP is basically bringing eBPF to network packet processing. So what it does essentially, if you go back to this model, if you're using XDP, you can kind of install small filters either here in generic case, so because it's it works for, you don't need to specialized hardware for that. You can do it in the network driver, or more and more network card manufacturers are now supporting eBPF and XDP natively. So if that's the case, it's actually you can install your programs, filter programs here. And this kind of protects you from attack traffic. So if you block bad traffic over here or here, you're not doing all this extra work to process the traffic. So like we try to like stay here, right? So like, and this is where we block traffic. So we install programs which are really fine-grained and fine-tuned to the attacks we see on the internet, and we try to block all these packets and only allow the good packets to flow. So we built so-called a distributed traffic filtering pipeline. So again, we have a lot of data centers, and each data center is continuously sampling samples of traffic to a centralized location, and this centralized location kind of like continuously analyzes and traffic and produces these eBPF XDP programs which blocks malicious traffic and redistributes them back to all the data centers, to all the servers in the cloud. And also we have like a smaller in data center version of the same thing, so we can kind of like process the attack faster. And what it allows us to do is, if an attacker comes in and starts attacking, like this system will hopefully fastly learn about how to block this attack and kind of knock it off from the network. But the nice property is that it will propagate through the centralized location, and if the same attack will be seen in any other data center, it will be already automatically blocked. So kind of like if we see attack in one place, we kind of block it everywhere. It's kind of, I don't know if there are Star Trek fans. I like to compare this to Borg, so you can adapt. Okay, so this is how we block traffic on the server level. Now let's take a step back a little bit and talk about application level protection, because we talked about the network level protection. What about like other things you can do to make yourself secure on the internet? I actually didn't have to go far. I just went to my spam folder, and like there is a message. Luckily, it's in my spam folder, so Google flagged this that I won an M1 MacBook, which is cool. If I go there again, thanks to Google, it tells me it's dangerous. So, but if it didn't, it has a nice like PDF I can click, right? And what happens if I click that PDF? Probably my machine will get infected, right? So. It's kind of malicious content, right? So this is your computer, and you run many applications there. And if you click that PDF, either like in best case, your browser session got infected. If you're logged in somewhere that these credentials might be harvested and reused. In worst case, like if the attack is more sophisticated, like you can be infected across several applications, and like in the worst case, like the whole machines would be infected, right? Again, how do you protect yourself efficiently? Well, you don't run anything, which is not very useful, right? So what you can do is you can run your application hopefully in a sandbox. So if you actually get infected, it won't be able to escape the sandbox. And actually, Chrome browser did a very good job sandboxing Chrome, not only across the different resources you access, but within the operating system itself. But it's still not be enough, because the sandboxing, it's just an arm race, right? Like sandbox is becoming more tight, but attackers keep finding new and new ways to escape from the sandbox. So what if like the most legitimate way actually not running the code on your computer, right? So but instead you can do it with Cloudflare, but other cloud providers support similar features. So you can actually run your browser on the cloud. So instead of browsing on your local machine, you can just connect to the cloud and kind of have this remote browsing session, and your actually browser, it feels local, but it's actually remote. It's actually running in containers in a cloud provider. And the nice property about this approach, no matter how bad the exploit is, like once you, like if you accidentally clicked a link, so that container gets infected, and yeah, but as soon as your session is over, like it gets shredded and destroyed, and it kind of has no actual impact to your machine. Clear? I guess this was mostly what I wanted to tell you today. So some conclusions here is, again, to protect from global distributed attacks, you kind of like need to build or use a global distributed defense, and vertical scale will eventually fail. It's an old phrase from Oracle, but we trademarked it. So the network is the computer. And actually, the internet is now your security perimeter. If you're building systems, applications, don't think about security perimeters anymore. Like think about what's now popular called zero trust architectures, where every request is validated against some kind of rules, and you don't like differentiate traffic coming from one IP address or the other, because it doesn't work in the modern internet, especially after COVID, where like many workers are remote, can work from anywhere in the world. Like I'm here in Madrid, I usually live in London, and I'm working this week from Madrid, and nobody even noticed it. Practice defense in depth. Again, we saw different layers of security here, from network to application. There are more, so don't just rely on one defensive layer. Try to build layers and different layers of the stack. And yeah, so basically you need security on all the layers of your infrastructure and all layers on your software stack. Thank you very much, and I think we have time for questions. Questions? You first.
For those of us who are just accustomed to systems, medium-sized systems, what type of data replication setups do you have in such large systems as the ones that you showed, like with distributed responses? We have never seen something like that. Can you just give us a picture of what type of data replication security measures you put in place in those setups?
Yeah. So with data replication, of course, like running this network is quite hard. And one challenge that we have, like, let's say if you're a user and you go and switch like a firewall configuration in your dashboard, that has to be propagated within seconds to all the networks in Cloudflare. And for this, we actually build a really fast distributed key value store, which kind of is able to, it's kind of the same as I described the DDoS thing. It's able to replicate fast from a centralized locations to all the data centers across the world. Again, you have to be smart here. And actually, I think we wrote some blog posts you can read online. It's called Quicksilver. It's not open source yet, but hopefully it will be at some point. But we kind of describe all the ideas behind that. But of course, there are trade-offs, right? So to build, you have to, at some point, you have to come up with the more complex systems, because that system is very fast, but it's not suitable for large pieces of data. It's only like a smaller key value stores, and it's kind of quite expensive in terms of replication factor, because everything is replicated everywhere, right? So like if you switch to other systems, you have a trade-off, like you have less storage, but like more latency of actually accessing this configuration. So it's kind of mix and match depending on the use cases. But it's kind of like this fast replication store is the backbone of everything we kind of need to distribute fast to all the data centers, including these XDP programs. And you ask about security measures. So the way how we learn about the attack traffics is basically we continuously send sample traffic for processing in the centralized location. So all our data centers report some sampling rate of some traffic, and there is like a huge engine. We continuously, it's also an arm race, so we continuously improving it. First it was based on like some heuristics, now it's kind of automated processing. We're also experimenting with AI and other stuff, but it can come up with a decision if the traffic good or bad, and if it's bad, it can quickly generate this XDP program which can like really reliably target it and block it on the network.
Well, thanks for the presentation in the first place. I enjoyed going down deep to the layers. You almost brought me back to my uni years. But I wanted to ask for those of us that are running, applications in the cloud, we would expect some of these, well, most of these techniques are already applied by the vendors we use and we rely on. What would be the things you would do on the high level to securize your systems? And like, what would be the main ones?
Mm-hmm. So first of all, like you expect, but you need to really check with your cloud provider, right? Because I mean, different cloud providers they state it explicitly, but they often tell you where their responsibility ends and where like your responsibility starts. And one of the things which I continuously see, both inside Cloudflare and even across the industry, people do not realize that if you run virtual machines, the operating system upgrades is on you. And for example, my day job is to ensure that Cloudflare always runs the latest Linux kernel. So we're kind of releasing a new Linux kernel to production almost every week. And this is, I have another whole presentation about it. And this is just because every week there are like a number of vulnerabilities from 1 to 10 are being patched. And like many people who run, they don't really, like usually it's like the Linux kernels is people don't want to touch it because it's prone to break-in, but people just run vulnerable kernels in the cloud and just they get exploited. So keeping your system up to date, especially like if you run on a VM, is kind of your responsibility most of the time, and this is what you should have primary focus on. I joke in the other presentation that specifically for Linux kernel, like I remember the good old like 2000 years where there were sysadmin forums and people like boasted, you know, like, oh, my server uptime is 2 years, my server is 3, how stable it is. Like it's not cool anymore. If your server uptime is more than 20 days, you're likely vulnerable and you'll get exploited. So like so this is where you need to focus, is building a system which is resilient to upgrades. And that, like even in Cloudflare, we have the huge network. Like I think our superpower is just being able to reboot servers all the time. Yeah, so but even like for regular software, also you need to keep up with updates. This is one thing. I guess the second part is what I mentioned previously. How do you connect to your cloud service? So again, cloud providers kind of provide you this old school secure perimeter approach where you build like an internal network, a DMZ of some sort, but like really embracing the zero trust setup in a very generic meaning of the term. This is where will make your resource powerful. So if you need to connect somewhere, it's not like based on your location and your IP address, it's based on the secure cryptographic credential that you provide. And basically almost every interaction with the system is validated across this cryptographic credential. So this kind of builds the security resiliency in any setup, I think.
Thank you.
Hello, thank you for the presentation. But I have a question about the slides that you put in the screen about Anycast.
Mm-hmm.
I was reading, but it is possible to do that on IPv4?
Sorry?
It is possible to do that in IPv4, or it is only in IPv6?
Oh, it's both IPv4 and IPv6.
Oh.
So yeah, you can announce IPv4, IPv6 addresses. Okay. It's basically how the internet works. Yeah.
Thank you.
I would say maybe adding to this, with IPv6 you have more flexibility, just because you have a lot. Like IPv4 is just freakingly expensive these days. It's like the next gold. You don't invest in stocks, invest in IPv4 address. Yeah, but with IPv6 you kind of like have, you know, like more flexibility in terms of like any small thing on your server can have a dedicated IPv6 address, but this kind of like the different sense. Yep.
Hello. I don't know much about networks, but on the CDN bypass attack without the egress tunnel, doesn't the attacker already know the IP when they, like, doesn't the CDN give you the IP when you ask for the URL, or doesn't?
No, actually. So when you put your resource behind the CDN, it takes over your IP address. So basically, let's say your service is example.com, right? If you put it behind the CDN, when you try to, like a user tries to resolve that through DNS, instead of getting your IP address, it will get the CDN's IP address. This is how basically the traffic goes to the CDN instead of your service. And only the CDN kind of knows your real IP address to forward it to. That's the whole point. Yeah, there is.
Hey, thanks for the presentation. Well, it's not a question. Can you talk about the risk associated to the public Wi-Fi networks and how can we mitigate that?
Tricky question.
Yeah.
there is like a lot of debate in the security community against that, against public Wi-Fi, you know, either really bad or not. I guess there are basically I'm just telling my own opinion on that, take it or leave it. The whole risk about public Wi-Fi is about what we call the last mile, the connection between yourself and the access point, right? And there are two types associated. Like here, if I see the university network, right? We have like the visitor network, which is just open, although it's behind captive portal. But what does it mean is, because it's open, like anyone with a sniffer can kind of sniff traffic most of the time. And it's also, there is what we use, the events, which is behind a password, which is a little bit more secure, because with this password, even though like everyone knows this password, with this password, it's still possible to establish a more secure session, which is not prone to sniffing. But because the attacker knows password, they can do a man-in-the-middle attack somehow, but it's kind of just more complicated. It's possible, but more complicated and more involved than just doing hijack network. So, yeah, that's basically, and like, yeah, like what does the network do with your traffic? Is it like sending it to the right position? But basically what we use in Cloudflare, for example, and you can use, because it's a public free app, we use Warp, which is a kind of VPN thing. And like even now, like wherever I go, I'm never worried about public Wi-Fi, because I just secure my traffic, like even though the outer network is not secure at some point, even if it's not password protected, my traffic from my machine is always encrypted and goes directly to Cloudflare data center. So I'm just not worried about that.
Okay, thank you.
Yeah, I always enable this application. And again, the thing is, like, this is where kind of zero trust comes into play, because I just have it always enabled, and I don't care if it's a public Wi-Fi, it's my home network, I'm just always connected through it, and I just don't bother about it. Any more questions? I have one question.
Also, thank you for the very interesting talk. I'm not very familiar with this technology, so I have a question on the server side security, or server level of abstraction.
My favorite.
Because you said that these expensive security options, they all saturate at some point. And the way I understood that you were explaining how you use the router inside of the data center, my question will be, is the router not at some point also overloaded with attacks? And also when you use the hardware filtering, is there also not an upper limit to that?
Mm-hmm. Yeah, this is a good question. So again, it kind of like depends on the hardware you buy. You buy a regular router, I would say even a switch. So what is a switch is a line card, which kind of like can switch packets between ports. It's very simple, right? You can buy a router with hardware filtering or some security capabilities, but that becomes more expensive, right? And you're actually not sure how that filtering is implemented there, because unfortunately most network hardware is now closed source, and like we've hit a lot of different limitation outside of security in the network hardware, which we couldn't fix, and we had to work around them. But eventually you don't know how, if that solution is implemented for huge internet attacks or just regular, right, ones. And how programmable is that? So basically what we can achieve with XDP, the nice thing about it, we continuously can update it and we can program it. So like we can target packets up to a particular bit in the packet. We know like this attacker traffic sends this bit and we can target it. Whereas even if you have the support in the router, not more expensive, it's kind of like yeah, you can't really program. You can do like basic filtering based on IP addresses and ports. It's not very flexible. So you can block like legitimate traffic as well. Again, it's not about like blocking an IP address most of the time, so because you can see legitimate traffic and attack traffic coming from the same IP address, from the same network. So you have to really fine-grain about it. And again, then what is the cost of upgrading that router later, right? you need more functionality, you'll have to buy more. So like our approach is kind of invest, like have the the most basic setup on the networking side. On the specialized, we can control and do most of the things where we can control on the open source side and programmable side. Yeah, and to the point, can a router be single point of failure? Actually, if you just use it as a switch with a single line card, the only single point of failure becomes if just the traffic like overloads the pipe. So it's not only about filtering the traffic, it's just like overloading the pipe, and there is not much you can do anyway.
Okay, so unfortunately, if it is quick, it's okay.
I'll try.
Last question, and I'll be quick. You say vertical scaling will fall eventually, but when will be a good point to say, I need to actually start vertical scaling because I can be living with an egg carton with my machine or a toaster? When will be a good moment on time? I mean, how many years or how many versions would you say to start growing up vertically?
Growing capacity, you mean?
Yes, improving your machines.
Well, I mean, it depends on the workload. Like, I'm not sure I can give you a generic solution, and we keep adapting even our internal metrics, how we evaluate it over time. So a long time ago, we were with just a simple CDN. So we had like one set of metrics. Now we do all these other things like zero trust and workers. We kind of changed the way how servers work. So we have a different choke point now. But in the basic level, what we do is we monitor CPU utilization and try to keep it around 80%. But we know like for other workloads, 80% is too big, and like the workload chokes on that point. For different types of workloads, you can like put it up to 90%. You basically have to find this checkpoint and kind of monitor it eventually.
All right, thank you.
Okay, thank you very much, Ignat.